Okay, the last section, chapter 4, which you're going to kind of go back to more with matrices. We sort of throw this last section in because it's kind of just an extra section that we're required to cover for this class. It doesn't go really neatly with too much other things, so we kind of put it at the end of the semester, so if we ever run out of time, this is one of those things that we could always throw out. Alright, but we're not. We're going to do it. Alright, so matrix addition. So basically this is going back to matrices. In chapter 3, we did a special type of matrix called the augmented matrix, which that matrix, the augmented case, was a matrix that represented a system of equations. And then we used the Gauss-Jordan reduction in order to solve the system of equations. In chapter 4, a matrix is just going to be a matrix that doesn't really have any meaning to us. It's just going to be a rectangular array of numbers. Alright? And so we're going to practice doing math with just regular matrices. Alright, so in 4.1 we're going to do matrix addition and scalar multiplication. So first of all, just to define a general matrix. This is not an augmented case, although you could do the same processes that were going to be used for these if it was augmented, if you wanted to. But like I said, this is the general matrix case. Alright, so in general, a matrix of the size m by n, right, matrix A we usually label it with a capital A, is just a rectangular array of real number values where you have your numbers set up, and they're just numbers, they have no meaning, they don't mean x term, y term, constant term anymore. They're just numbers that are arranged in a rectangular format. Alright, where we have m rows and n columns of these numbers. Right, so that's the dimensions of the rectangle. Right, so m is always always rows by columns in our matrix A, and then you have so many numbers involved. And so a lot of times we're going to ask for a specific number in the rectangular matrix, and to do that we indicate it using a specific type of notation. Alright, so my matrix that we're looking at, suppose we have some matrix A, right, that we've been given. So A is the uppercase A is my matrix. And so when we use the notation, and sometimes different books do use upper notation versus lower notation, but the notation is the lowercase a represents I'm in matrix A, and then there's two numbers. There's an I is a number, and then there's a J is a number. So I is a number and J is a number. And so what that symbol, right, math is a language, we use our own terminology, right, so what that symbol, you have to recognize what this means, is I want the number, or the entry, found in matrix A, right, the lowercase a tells me what matrix I'm looking at. And then the numbers, the lower numbers there tells me the row and column in my matrix. So row I and column J. It's kind of like bingo, right? I don't know, maybe you've played bingo, right? BI, alright? So it's in row, whatever, B and column I. And so this is our matrix notation. So this is what's packed into this notation is we've got a bunch of numbers in a rectangle, and I want a specific one of those numbers. Well, to do that, I have to figure out, well, what matrix am I in? In that matrix, what row and what column am I looking for? And so that's what those numbers. So row I, column J. Alright, so we're just going to practice some dimensions and then finding numbers in matrices. Alright, so I've got my three matrices here. The first thing is what are the dimensions of each matrix? So my matrix A has 3 rows, 2 columns, right? This would be row 1, row 2, row 3, column 1, column 2. Alright, so it is a 3 by 2 as its dimensions. Matrix B has 2 rows, 3 columns, so it's a 2 by 3. And matrix C, 2 rows, 2 columns, so matrix C is a 2 by 2. Right, then find the following values. So I'm just going to write them up here. So I want A, 1, 2, A, 3, 1, B, 2, 2, B, 1, 3, and C, 1, 1. Those are the numbers I want. Alright, so the lowercase number, A, so the first one is a really weird A, but that is an A. sub 1, sub 2, and so it's not sub 12, it's 1, 2. And so this means I want to be in matrix A, so I look to matrix A. I want the number in row 1, column 2. Row 1, column 2, that would be this number 5, negative 5. All right, then I do the same thing for the next one. I'm in matrix A still, all right, that's the lowercase a. But now I want row 3, column 1. So row 3, column 1, well, that would be the negative 4. It's where the row and the columns meet. All right, the next one is B22. So B22 would be I want to be in matrix B, row 2, column 2. Well, that's my negative 6. All right, and then B13, well, B row 1, column 3. Well, that's the number 2. All right, then the last one is C11. Well, that's in C. Row 1, column 1 would be the very first number 4. And so that's what, a lot of times we'll ask for that, because it's just easier to write a question sometimes instead of asking for the entire matrix. What we ask for instead is a single number from my matrix. Instead of I want all of matrix A, well, I just want the number in matrix A, row 1, column 2. And that's the notation that we use. All right, some special matrices. All right, the first special matrix, which we're actually going to use this more in the next section, but it's introduced here in 4.1, is a row vector and a column vector. All right, a row vector means it's a matrix with a single row, and a column vector is a matrix with a single column. So the easiest way to kind of recognize these would be just giving you an example. All right, so suppose my matrix A is the row vector case. So that means I've got a single row with some numbers in it. So 3, negative 5, 10. All right, so this would be a 1 by 3. That's a row vector. There's a single row and then 3 numbers in it, right, which would be my 3 columns. A column vector would be the exact opposite of that. So suppose B is my column vector. It's a single column with some numbers in it. All right, so this would be an example of a column vector. It is a 4 by 1, right? I've got 4 rows, 1 column, and so column vector. And we'll do more with the row vector and column vector in the next section. This is how we first introduced multiplication, right? Row vector, but those are our special matrices. All right, so the last one for this video that we're going to talk about is the special matrix, the square matrix, which we've seen square matrices before. Whenever I have a matrix that have the same number of rows as columns. So a square matrix would be something that's an M by M matrix, or N by N. All right, I have the same rows, the same columns. So an example would be something like a 3 by 3 or a 2 by 2. So 3 by 3 would have 3 rows, 3 columns, so there'd be 9 numbers. And that would be an example of a 3 by 3, right? I've got 3 rows and 3 columns. 9 numbers in my matrix altogether. And so square root, and for most of ours, they'll be 3 by 3s or 2 by 2 would be the other case that we typically deal with. Alright, so that would be a 2 by 2 example. I've got 2 rows, 2 columns, 4 numbers altogether. Alright, so our special matrices. So we'll stop there. We'll get into matrix addition and subtraction in the next video.